All right, everyone. Let's go ahead and get started. I I hope too many people haven't just been scared off by the midterm. But let's see. Before we begin, what was your general feeling of the midterm? We don't talk about the past. Okay. Well. Okay, but just give me just like a couple of minutes. How many of you thought that it was pretty reasonable, like reasonable level of difficulty?
How do you define reasonable?
Like you felt energized by the exam.
Energized to do what?
Positive, negative.
And myself, not really a lot of positive things.
Positive energy of like, you know, yeah.
The first 30 minutes I was reading the setup part.
Yes.
For sure.
Just to understand
Yeah.
what is going on.
And that is intended. That is absolutely, that's why we wrote so much, so that there would be plenty of, cross-verification opportunities, right? All right. And I do want to remind everyone who just got here that we do have a deal in this class, right? You guys all have to show up by 6:10, and then we start at 6:10, okay? All right. But, okay. All right. How many people just felt like it was too hard? Okay. Few people. How about way too hard? I see.
I always go for the option to make.
I see. Okay. All right. And then a lot of people who just didn't have a strong opinion about it, apparently. That's cool.
I had to talk to my therapist about it. So.
Okay. Okay. That was not the intended. That was not the intended intention of the point of the exam. But all right, here's the real question: how many of you kept thinking about it after you left? Yes. All right. My work here is done. That is the actual main intention of such an exam. Excellent. Yes.
I'm gonna add though, like it was hard in a sense, but at least for me, it was a good challenge. Like I know I didn't do good at all, but the challenge itself was something that I'm proud of myself.
All right. Good. I like to hear that. Yes, all of you. You should all feel that. Feel that like, yes. Yes.
For me, I also felt like it was a really good challenge. Like it really stretched my brain, but I just felt like I wanted my brain to get like actually stretched, and then I ran out of time, like before it actually got there.
I see. Actually, yeah. I'm just curious. Can I get a just show of hands again? How many of you felt like you just wished you had more time? Oh my goodness. Okay. All right.
Can you just do a questionnaire of the depression level after this class and assign grade based on that? Like, the more depressed you get, the more grade you get.
No, not at all. No. I fundamentally disagree with this idea. All right. Like, I actually want you guys to feel like all of you felt challenged, and I want you to really lean into that. Like that's the whole point. The whole point is to feel challenged and stretched, and to really see what you're capable of, right? That's the whole point of this class. Yeah.
One thing I wanted to complain about.
Yes.
And is like the design of the paper and like the location of like the text. I feel like if I got like the instruction that I could rip it off beforehand, because I was just spending so much time flipping, back and forth the exam, which I feel like I wasted actual time.
Oh wait, hold on a second. Do other professors not let you rip stuff out? Is that a real thing?
Usually people don't rip it out.
Really?
There's no necessity.
Oh yeah.
Usually the
Usually
question is
there's
like
like
with the
a lot of space
I
underneath
see.
every subject.
Okay, anyway, yeah, let me be clear. You are always allowed to rip stuff out of your exams. We will always bring a stapler so that you can staple your exam back together. I thought that just went without saying. Like, why would anyone prevent you from ripping papers out of the exam? Yeah.
I went with a strange approach because there were so many papers where I kind of just started writing like a diary entry about the test. Like
Okay.
I was like, I don't really get this, so I'm going to try this, and then but I ran out of time to like actually make it make sense.
I
So
see.
just feel bad for whoever grades mine.
Okay.
Do you get partial credits for that?
We will aggressively try to give partial credit, but obviously I can't promise anything. Like, I don't know what that actually looks like, so I cannot promise you. Yeah. Yeah.
I did the same thing.
Okay. Let me ask though. Let me ask. I want, and please don't feel like you are stepping on any other student's toes. This is just for my knowledge, okay? And this is the most efficient way. How many of you felt pretty confident about how you did on the exam? Okay. So one person? Seriously? Can you raise your hand really high if you felt pretty confident about the exam? Okay, one person felt really confident. Okay. All right. Okay. No, that's great, man. I'm really happy. I'm really happy to hear that. Okay, stop. We're not going there. Okay, all right. So harder than I thought it would be. Okay. It's so hard for me to estimate the difficulty of the exams that we make. Yeah. Well, we are currently scanning the exams in because the scanner is so broken. But do you have a suggestion or?
Yeah. Based on the participation that I saw with the question that you asked, I think it should be done by tomorrow night.
What?
No. We are actually going to try to give you points. Like that would be true if we were like wrong. But we're not going to grade it like that. Okay? That's not the way we do things. All right? We want to see the ideas you guys had. Yeah.
Out of curiosity, I know you guys came up with this question originally, right?
Mm-hmm.
How long did it take for you guys to actually discuss, like from you came up with the idea to validation to solving the actual problem?
Yeah, okay. So again, I do not want to make you guys feel bad, but like the rule that we have is that when someone comes up, so me and the TAs, we really have a lot of fun with it. We come up with problems, and the rule is, if I can solve it instantly, then it is allowed to be on the midterm, okay? And only, and if it, and if it takes any of my TAs, for example, longer than 60 seconds, then it's also not allowed to be on the exam, okay? So 60 seconds is the threshold. And then we try to make it simpler, actually, over time. So often the problem turns out it's a little bit too complicated in the beginning, and then we simplify it. So this was a result, actually, of several rounds of simplification, the version you guys got. Yeah?
Just a suggestion for, like, at least for the final and for the next quarters, if you could, it would be nicer to give the students more than one sample midterm. I think, at least for me, like, I rely on that one just to get familiar with the setup part of the midterm or final. So it would be nice if we had more
than one?
Yeah.
Okay, all right, we can do that. Yeah, we can do that. I often think there's like some trade-off, right? Where like, how much am I burdening you guys with stuff to do versus the utility from it? But yeah, multiple sample midterms is not a problem. So okay, so please remind me again. So for the final, we'll give out multiple sample finals. Now, the one thing is that I cannot give you guys solutions to all the samples, okay? Because we don't necessarily have solutions to all to all of the finals because we don't typically we don't give out solutions, right? So is that still useful to give out?
Oh yeah.
Yeah. Okay.
The fact that we're gonna sit down and think about it, I think.
Okay. Sounds good. Yeah.
I also felt like the practice midterm wasn't a really good indication of what was on the exam because the way it felt, it made us feel like it was going to be covered more on like the stuff at the beginning of the class, like the DSMs
Mhm.
till like the pumpkin lemma.
Mhm.
So like when there was stuff on PDAs we covered, it was like more vague and like I guess what we prepared for or thought of initially.
I see. So actually, here's something, and again, I'm just gonna how many of you guys realized that the midterm was more about DFAs than about PDAs? Some of you. Okay. Very good. Very good. Yeah. So I agree that it wasn't super that was the challenge of it, is to realize that even though it looks like a PDA problem, it's actually a DFA problem. But a lot of you guys did, so I'm very happy to hear that. So it's, but I still hear you. But that was always actually our intention. Yeah. Yes.
And actually, it felt like the material was enough. Like even if I didn't have that much understanding of like how things work, literally reading the beginning was enough for what I was able to do.
Mm-hmm.
But it just took so long to read that there was not like a lot of time to do.
Right. Right. Yes.
I did have a recommendation for the future as well. So this one only had one question.
Yes.
That might have been also like hard to read just because it's just one big bulky question. I think in like the practice midterm, since it had two questions, there were two benefits. Like one, the benefit was like shorter read time, and the second benefit is that it's split into multiple categories. So if your strengths is really like GNFAs.
Right. So let me just pause you right there. So this is just really funny, okay? Every year, right, when I have two questions, people are like, the real issue, and my suggestion for the future is just have one question, okay? And then whenever I have like a short description, then people are like, listen, you really need to have a longer description to help us clarify the issues that are not clear to us, right? So I appreciate you saying what you did, but it just continues the pattern. I actually do think that the one question is still the right sweet spot. Based on everything I've seen over in the past years. But I do appreciate your input on that. Yeah. Yes. Sorry.
I actually enjoyed the exam itself. My issue was, like just a skill issue. Like it.
Okay.
Yeah. Like once I like read it and was like, okay, I know what's going on, and then like the other page came, which if nobody else knows, the CAE exam didn't have page 3. So
yeah, that's a huge problem. That's ridiculous. Yeah.
So that sucked. But once that happened and I read it, like I was having a little bit of fun.
Okay.
But yeah.
Okay. Yes. Sorry.
Also, like I feel like the difficulty of the practice midterm is way too easy compared to the actual midterm. I don't know if you feel it. I know you always instantly solve it, so it might not be differentiable.
Yeah, actually, it really.
But to us, it's actually a large difference.
Really? So all of you guys felt like the practice midterm was way easier?
Yeah.
Really?
Yeah.
Okay. Interesting. Okay. All right. Always hard for me to figure that out. All right. Yeah. I mean, it was not designed to be harder at all. It was designed to be, in some sense, easier because it only had one problem. But I guess didn't quite work out that way. Well, no. I want to remind you guys, the actual description was like 2/3 of a page. Everything else was just to help clarify, like by giving you guys examples, giving you guys, like, by the way, defining a configuration, right? Like that was totally unnecessary, right? Like we didn't have to give you that. It was just a huge hint that I hope was helpful for a lot of you,
Really helped.
right?
Not having
So.
page 3 might have helped because when I read the exam, I was like, oh, there's not that many pages. And then I was like, I think I know how this works. And then I got the other page and I was like, oh, I totally thought wrong. And then it kind of
Right.
helped.
Yeah, so the whole point of that additional pages was to clarify what you were already told. Like the very beginning of the exam actually had a full description of what the machine was, right? The only point was to give you guys, so you didn't have to ask, so you didn't have to so you could actually see examples and see what's going on. Yeah.
You said the final is going to be split into two parts.
Yes.
Is it going to be like one part similar to midterm, the second part different? Or?
Well, the only way in which it'll be, so first of all, we're doing this for the first time this year, just to let you guys know. This is not the way we've done things in the past. There are reasons which I won't go into right now. But we will have on the Monday of week 10, right, in class, the first part of the final. It will be, honestly, it'll probably be a little more standard. We will give out practices of what that will look like. Yeah. And then there will be a take-home final, which is the rest of the week, week 10. Okay. Well, you'll have unlimited time, so at least time will not be an issue. Yeah. Let me just 1 second. Yeah.
So we're not going to have class on Wednesday.
We are.
Oh,
We absolutely are. In
though we
fact,
took the final on Monday.
even though you took part 1 of the final Monday, and the rest of the final will be due on Friday.
Yeah.
Actually, the Wednesday, the final lecture of this class, is like the coolest thing ever. So, in my opinion, I love teaching it, and you guys will figure stuff out. Yeah. Yeah. Yeah.
So there's no finals week, like we don't.
There's no final on finals week.
So the scheduled time we just ignore.
You can just chill out. Yeah. All right. Okay. Are we all done? I'm sorry for making you relive it, but I hope that you guys actually did enjoy it. Okay, one more comment. Yes?
One thing, I was actually really, really happy that we had those pages because they are the only thing that actually made me able to solve the problems. I
Okay.
was super happy. I was looking at the examples constantly, going through them multiple times.
The examples, right? Yeah, okay, good. That was why we put them there, because we think that for so many people, it's just so useful to just see an example, right? Like when you see an example, things click. So that's why we did that. Yes?
Question about the homework.
Yeah.
Is there a reason it's due on Friday and not Sunday?
Is that a request?
No, I'm just
okay.
out of curiosity, and then after I hear the answer, I might.
You might. Okay, so the only issue is this. I have a terrible memory, and the TAs are not here right now. So, okay, would you guys like to have an extension to Sunday? Yes? All right, okay. All right, so we will extend the deadline to Sunday night. However, I will forget this, so please, you are the designated person, okay? You.
No, I'm not English. I will remind you tomorrow.
Okay, yeah, just send an email to me and the TAs,
You got it.
okay? Because I will forget.
Guys, if I forget, I'll just.
Yeah. Okay, all right. One more person can volunteer to be the backup reminder person. Anyone want to be the all right, backup reminder. All right, very good. Now we got you covered, okay? All right. Well, again, I am really glad that you guys felt challenged and that you guys kept thinking about it after the exam. That makes me happy. That's what we're going for always. Okay, I guess one more question. Let me ask you guys one more question. And the TAs are going to kill me for asking this, but let me just ask, because I do want to actually understand what your preferences are, okay? So for the final exam, part 1, that will be on Monday of week 10, right? I assume none of you have classes at 8 p.m., right? Would you actually prefer that we stay longer and allow you guys to work longer than 2 hours?
Yes.
Okay, I see some, and sorry, first of all, for any of you, would it just be impossible because of other commitments that you have in life, which is very reasonable. Please raise your hand if it's impossible because of other commitments. Okay, that's a veto. All right, so then that's it. Yeah.
Is that going to affect the difficulty of
No.
the exam itself?
No.
So it's just like extra time?
Just extra time. Yeah. Yeah. Okay. Okay. No, that's not fair then. I mean, people are allowed to have lives outside of CS181, and I do understand that. And you know, we're only scheduled to 7:50, so you know, I'm going to give you guys an additional 10 minutes, and I think it's not reasonable for me to ask for more. And it's hard 8 p.m. constraint for the people who raise their hand. Hard 8 p.m. constraint. Okay. All right. That is what it is then. I would like to give you guys more time, but I don't know how else we can do it. Obviously, I can't do it beforehand because some of you probably do have classes right before, right? So we cannot do that. All right. Is that a question or thought? Okay. Any other suggestions? You know, I like to work with you guys, but there are limits to what I can do.
Maybe if you pump some time.
Time pumping lemma. Oh my goodness. You know, that along with, you know, every day, wouldn't it be awesome if we could wake up and clone ourselves and then just like a recombine at the end of the day? That's my dream, you know. Actually, do you guys know Calvin and Hobbes?
Yes.
Yeah, there's actually a Calvin and Hobbes about that, which is awesome. Anyway, all right. If there's nothing else, shall we get back to the story and where we were? Yeah? Anything else? All right. Let's get back into it then. All right. So, what happened last time, right before the midterm, was that you guys came up with a different machine, right? And the machine still had like a DFA core, right? Just like our stack machines had an NFA core. In this case, we're going back in some sense just to deterministic machines, right? But now, the way that you guys described it is that we still have like our stack that's, you know, one-way infinite. But now we have a pointer that points into the stack, and you can just tell the pointer to go up and down, right? That was the main idea of what you guys came up with, right? So I'm just going to make a very cosmetic change. And this is just for historical reasons. So let's just take this stack and just turn it on its side. So we will have still a one-way, like infinite, infinite memory, right? We'll still have a pointer that points into it, okay? Instead of calling it a stack, because obviously it's not a stack anymore, we can move the pointer around. For historical reasons, we shall call it a tape. And it's still true, right? All of you have seen a cassette tape in your life. Is that true? Is there anyone here who has not seen a cassette tape? All right, good. Good, good, good. I'll feel very sad. Well, one day, you know, I'll ask that question. People are like, well, what are you talking about? What is a cassette tape? Anyway, all right. Yeah, and I'm old enough that my first computer actually we would store programs on a cassette tape. So no, this is even before that. So before that, it was literally just a cassette tape, like the same thing that would record songs, and you would just plug your computer into it, and then it would speak in its own language. And at one point, just from hearing it, I got good enough that I could actually just make a noise into my tape machine. It would actually come out as a string, like. But anyway, that's just neither here nor there. Yeah, so we have our tape, okay? And then for similar historical reasons, the pointer into the tape, we're going to call the head. Okay? So again, the head is just a pointer that points into the tape. Okay? We have our tape alphabet, right? Which we'll still denote by gamma, right? We will now definitely insist that the tape alphabet contains the input alphabet, right? And if you remember another thing that you guys decided last time was that without loss of generality, we can say that maybe first of all, there's always a funny symbol that's in the tape alphabet. So this is also a subset of that. And let's say maybe the beginning starts with the funny symbol. And then whatever the input is preloaded onto the tape. Because why not? Okay? And then what about what's in the remaining cells of the tape? Again, you guys had the thought that we should just have like a blank symbol. So there's also a special blank symbol, which is in always in the tape alphabet. Let's say those are the only two required things. Okay? So when we get to the end of the input, we just have a bunch of blank symbols. They go on forever. And that's how the machine starts, right? Makes sense? Any questions about this? All right, very good. And then, yeah, we can tell the head to move left or right? And at any given moment, our machine can read what's underneath the head, use that to make a transition, and also overwrite whatever is there before it moves either to the left or to the right? And let's just make a rule that if you're already at the leftmost spot and you try to go left, it just stays there. Reasonable? Cool. So this is the machine that you guys came up with, right? With some slight maybe guidance on my part, but really not. Really was all you guys thinking about this, right? So what you guys did last time was reinvent the Turing machine. So this thing is called the Turing machine. The only thing that's slightly non-standard about our version is just the funny symbol at the leftmost part of the input. A standard Turing machine does not have that, but that's fine. We're going to work with the version that you guys came up with. Okay. So let's go ahead and define it. So we're going to have our Turing machine M. As usual, we need to have a tuple, right? So anyone want to help me get started? You just want to nail it down, get it exactly precise. Yeah. Yep, absolutely. So we're going to have our set of states. Okay. Do you want to keep going a little bit further? Absolutely, right? Yeah, we're going to need like a starting state, right? Yeah, actually, so that's the only thing that I wanted to pause for a bit. So like accepting states, let's actually just take a moment and and sort of rethink that a little bit later on. So maybe I'll put that as like a question mark. And we'll kind of think about it later on. Again, we already have our input alphabet. And now not the stack alphabet, but the tape alphabet. Right? Okay. Now, of course, the big thing that we haven't done yet is the delta function, right? We know it's going to be a little bit different, so maybe let's think about that first. So thank you, definitely worth the token. Do you want to get us started on the delta? Or question, yeah.
So we said the output is subset of the tape alphabet.
Yes.
Why not remove the input alphabet in general and just go with the tape alphabet?
Good. So we still will always need an input alphabet because the machine has to like take some string as input, right? And that string will come from the language, and the language is always defined as a subset of sigma star. So that's the only reason. Yeah, but perfectly reasonable question. What do you guys think about our delta function? How are we going to do that? So it's going to be a little bit different now, right? It's not going to be exactly like a DFA. It's not going to be exactly like a PDA. It's going to be slightly different, but similar in spirit. Again, it is going to be deterministic because we are just doing that. Yeah. Yep. Good. So we're currently in a state, right? We see a particular tape symbol right underneath our head, right? Excellent. And that's it. That's all we see, right? Okay. And then what about on this side? What will be here? Hmm? Sorry, say one more time. Good. Yeah. So definitely there'll be a new state, just like always, right? Of course, every transition can move to a new state. And there can also be a new tape symbol, right? So another tape alphabet will be here, right? Excellent. So those are two things that definitely we need. And what else? What else can you? Yeah, and you can just move it, and you can just move the head, right? So they'll just be left or right. And let's just say that it's not allowed to stay where it is. So it just has to move either left or right. Okay. That's actually it, right? It's actually even simpler in some sense than a PDA, right? So we've actually made things even a little bit simpler by moving to the Turing machine. Yeah, good. So first of all, thank you. Definitely worth the token, right? And now, yeah, we kind of have to think a little bit about accepting states, right? So recall that, well, even PDAs had this issue, right? That like you could pop and pull for push and pop forever, right? And like wind up in an infinite loop. That's also, of course, going to be true here. You could just keep moving left and right. Or you could, in fact, just keep moving right forever, right? That's kind of like pushing forever, right? So those are things that are possible. But one of the things that we decided was that we would actually preload the input onto the tape, right? So now there's no such thing as like reaching the end of the input anymore, right? There's just stuff that's on the tape. Whereas in PDAs and DFAs, if you ended the input in an accepting state, then you accepted, right? Now we don't really want that to be the rule anymore, right? Because there is no such thing as just getting to the end of the input anymore, right? So what should we do? Like, what could we replace the accepting states with? Like, what's another alternative for such a thing? I see some like microscopic hands. Yeah.
First, like a question, like
yeah.
So saying if it's like you can leave the accepting state, can it like essentially loop forever?
Right. So like if we stuck with just accepting states, right? Then like you could imagine an accepting state with a self loop, right? And like move right. And then we don't know, like, does that machine actually accept? Or does it just loop forever and like reject as a result, right?
Maybe you could make it just like as soon as it like touches an accepting state, you could just have it immediately accept.
Okay, excellent. Thank you. Totally worth the token. That's a really nice idea. Why don't we just have, in fact, just to make things simple, how about we just have one accepting state, right? So we could just have Q accept. That's a member of Q, right? And basically, as soon as you touch this, right? As soon as we reach this, let me say this. We accept immediately. Right? That's a perfectly natural way to resolve the issue, right? We can just have a special accepting state. And thank you, definitely worth a token. Anything else? Any other, like, yeah?
Would that be like, how would that differ from having the accept state like on the tape? Like you leave this character, you're done. Like would those be different?
Okay, you mean like having like a special accepting character,
Yeah.
which as soon as you write it to the tape, then you immediately accept? That could be another way we could do it, you know? But an accepting state is in some sense even more natural, right? It's just like a place in the control where you say, hey, just stop. I'm done with my computation now. I'm just going to accept now, right? So yeah, totally valid alternative, but I would argue this is a little bit more natural and simple, right? Yeah.
How would we decide when to reject?
Yeah, so okay, what do you think? What should we do for that? Yeah, why not, right? And in fact, why don't we just make it 1 again? So let's just have Q reject, right? And again, this is like as soon as we reach reject immediately, right? That works. And yeah, thank you again. Definitely worth a token. And now we have these like special thing in our Turing machine, which is we have these special like halting states, right? There are just 2 of them, but they're special ones that as soon as we see them, we immediately halt the computation, right? Yes? Sorry.
Couldn't we also reject when we have like an empty tape and nothing to like basically transition?
Well, observe that our delta function actually transitions on anything that could be in the tape, including the blank symbol, right? Which, by the way, we haven't added to our definition yet, right? So I said that we have to have a blank symbol. So I'm just going to use your question as my excuse. So let's just add that also to our definition, right? So you guys came up with 2 different things, the blank symbol and the special funny symbol. So let's just say these have to be members of gamma, and this is, you know, written to leftmost tape before the input. And this is the blank symbol that is preloaded to the remainder of the tape, right? Yes?
If I understand correctly, this machine is able to loop indefinitely without ever reaching a halting state.
It can, yeah.
So is that another case for reject, maybe?
Yeah, good, very good observation, right? So like there's this observation, which is that a Turing machine can accept, reject, or let's call it loop, right? Where I'm going to define loop to mean, you know, not halt. Okay, so when I say loop, I don't mean like necessarily that it is a loop. For example, it could be move right forever, in which case it never like actually loops as such, but it just never actually reaches an accepting state or a rejecting state, right? So yeah, so there are actually 3 possible things that could happen with the running of a Turing machine. Now, as usual, right, we will still define the language of a Turing machine M to be all strings x and sigma star, such that M of x accepts. Right? This is the way that we define things always. Right? So in that sense, looping is similar to rejecting in the sense that it's not accepting, right? But you're absolutely right that it's like a different, qualitatively different thing that a machine could do, right? So yeah, that's a very important observation, actually. Yeah, thank you. Also, definitely worth a token, right? Yes.
Question like is since it's still on a DFA, does that mean like out of every state, like there's only one transition on a FFA?
Yeah, like the delta function, for every input and for every symbol, there's only one transition that goes out of that.
So like if there's only like a finite number of states and like a finite number of transitions out of these states, like, do we know like after a certain amount of steps that like if you haven't halted yet, that the machine is looking forever?
Okay, I really like your question. So your question is, can we guarantee? Am I understanding your question correctly? Like, can we somehow like guarantee that a Turing machine doesn't halt? Something like that?
Like will we know after a certain number of steps?
Yeah, for example, like, let's say after a certain number of steps. It's a very natural question, right? It's actually something we're going to be thinking about a lot. I claim that it's very non-obvious what the answer to your question is. It's definitely worth a token. Really nice idea. Really nice thing to think about. Okay, maybe let me ask everyone, actually. She raised an interesting question. Is it true that like if a machine, let's say your input is of length n, and the machine ran for 2 to the n steps, does that guarantee that the machine is going to run forever or going to halt? Do we know? Any? You can raise your hand and tell me why. Yeah?
Do you think we can make a Turing machine that can tell us if a Turing machine is going to halt?
Okay. Before we get to that meta question, which is a really interesting one, but that's kind of like anticipating stuff. Just think about this specific question, right? So can you give me an example of a Turing machine? Like what could it do so that even if you knew that it didn't halt after 2 to the n steps, we still don't know. Maybe it'll still halt later. Like, what might it do? You have a thought?
I mean, there are like a lot of things that grow significantly faster than 2 to the n.
Mm-hmm.
And so like, I mean, like there are like you could have a Turing machine that does like graph problems that grows like so much faster than 2 to the n. So like at 2 to the n, it's not done, and it needs.
Okay. All right. You guys are jumping a little bit ahead, which is okay. Different people have heard different stuff about Turing machines before. So let me just pause that particular discussion, because as of right now, let me explain to you why you're jumping ahead. So as of right now, right, a Turing machine is just the next in our evolution of machines, right? Like we had DFAs that had regular languages, we had PDAs that had context-free languages, and now we have Turing machines, and we don't know what they can do and what they can't do, right? And that's where her question comes from, right? So like, is there a pumping lemma for a Turing machine, right? And it's a very natural question. Like maybe there is, right? Maybe there isn't, right? If someone sees an immediate reason why it can or may or may not exist, then you should let me know. But otherwise, I think we just agree that it's an intriguing question, right? At the core, that's kind of where you're coming from, right? Like, is there like a pumping lemma? Is there something like that, right? That might be true for a Turing machine. So yeah, very interesting question. Let me just say that this is the definition. This is kind of the end of the definition, right? There's nothing else that we need to define a Turing machine. Now we've gotten everything we need, right? It has like longer stuff in it, but if you really look at, these are all like trivial things, right? It's like, okay, accepting and rejecting state, special blank symbol, special beginning of the tape symbol. Like they're not that interesting. So I would argue it's actually, if anything, maybe even slightly simpler than a PDA, right? So we've actually, it's a really, really simple machine. Seems like a very slight modification of a stack machine. It just lets you go both up and down, right? Both left and right when we look at it this way as a tape, right? Yeah.
This is kind of going back to the question you asked earlier.
Yeah.
But it may not be exactly what you were looking for, or just like a Turing machine. If you have like 2 to the n states, or like 2 to the n plus 1 states, then you can just like go through it 2 to the n times, and then it'll keep going at least one more time.
Okay. Yeah. Right. Sorry. I guess.
But like that's not like any arbitrary n, so it's kind of.
Right. So remember, like there is a set of states here, but that set is finite, right? So like the size of Q, let's say, is K, and then yeah, let's say that it was 2 to the Kn, you know, like so that you can't have like different states, right? But okay, but you know what? Let's just like put this aside for a minute, right? And it's definitely at least an intriguing question, and what we are really after now is trying to understand, okay, we made a little change. How much more power did we get out of this thing, right? Like how powerful is this? And actually you guys had a bunch of nice ideas about that in the last lecture. So let me just remind you of the questions that you guys came up with. One at a time, okay? So the first one that I want to remind you guys of is like the multi-stack, or in our new nomenclature, the multi-tape Turing machine. Okay. So let's imagine that we have our control, let's finite control. I'm just going to call it a DFA again, even though this is kind of, I should put it in quotes. It's not really a DFA anymore, but it's like a DFA, right? But now, let's say instead of pointing to a single tape, it actually has 2 tapes. So let's think about this as being kind of like the main tape. And like maybe this is the one that starts with the input on it. And like, let's say this is the work tape. And it just starts all blank. Right? Yes? Yes. So the main tape also will have blanks. Sorry, should have made that clear. Yeah. So they're both like, you know, semi-infinite tapes. One of you guys mentioned that actually as soon as you have 2 tapes, you could kind of think about like gluing them to each other, and then it's kind of infinite in both directions, right? But this is even more powerful because you actually also get to have 2 different pointers, right? 2 different heads that you can move independently. Like you could say, this guy, move right, this guy, move left, right? And that's just allowed in our multi-tape Turing machine model, right? So let's just give it this a name. So this is the multi-tape. Okay. So the question that you guys asked last time was, is it equivalent? What do you think? So suppose I only have 1 tape versus having 2 tapes. Obviously, if I have 2 tapes, that's as powerful as having 1 tape. I can just ignore the work tape, right? So clearly, this machine can do anything this machine can do. The question is the other way around. Can you simulate a multi-tape Turing machine with just a single tape, right? And you guys actually did start to come up with some ideas about that last time. Yeah, what's your thought?
If it's only 2 tapes,
Mm-hmm.
can you use like the left of the $sign? Because it's technically like infinite on both ways, right?
No. The way that we define the tape is that it's only semi-infinite. It's only, it actually has like a leftmost spot. And like there's a hard boundary here. So our machine, if the head is here and you tell it to go left, it just stays here. Yeah.
I guess you will have to stick your workspace somewhere else to the right, right?
Okay, yeah. So, okay, she has a very natural idea, which again, you guys actually thought about this the lecture before. The lecture before the midterm, right? Which is definitely worth a token though, right? Which is the idea that maybe we could have our funny symbol. We have x1, xn, let's say, right? But then instead of having a blank symbol, we could have another funny symbol, let's say hash. And that's like the separation of tape symbol, right? And then we just have our blanks afterwards, right? And that definitely gets us started, right? So totally worth a token. What's wrong with this idea? Like it doesn't quite capture it. Like there's some information that is not present here. Yeah, in the back. Yeah, we also need to keep track of the other head, right? The head information is missing here. We only have the one head that's pointing in here, right? So do you have a suggestion? How might we keep track of the head? Okay, that's actually a really cool idea. Okay, so he's suggesting something very, very interesting, which is that he wants our gamma to actually be like, let me maybe call it gamma prime, like the new gamma that we're making, is going to be our old gamma, but then cross 0, 1. Okay, yeah, like no head, right? Maybe NH for no head. Maybe head 1, because there are actually two heads, right? So maybe head 1 and head 2. Something like that. Is that what I mean, slightly modifying your idea. I think maybe you're thinking like the current head would keep track of where but this way, because remember, we're gonna have to move the head around, right? Yeah. So, so this is a really cool idea. What this is saying is like we can actually think of each cell of our tape as actually consisting of two cells, right? One cell that actually holds the value, and the other that just tells us where the head is, right? So and let me actually kind of draw it this way. Okay, yeah. Okay, give me 1 second. Let me just adjust my previous drawing. Right, this was our two-headed Turing machine, right? And if you want to like visually see his idea, you can think about it this way, that now it's kind of like each slot, right, in our tape has, so this is the single, sorry, this is now the single tape Turing machine. That in our single tape Turing machine, because we think of a particular slot as having both a place where we can put the original symbol and something else, right? That we could have this like little note area, this like margin, right? And then we can say, okay, actually head 1 is here, and then maybe head 2 is here, right? And then wherever I didn't put is like a no head. I'm not gonna write no head, no head, no head everywhere. But think about like, if I don't write anything, it means the head is not there, right? Very cool, right? Once we've done this, then we can keep track of where both heads are. Yeah?
Question, so how would we know where do we start our blanks? Because like xy to xn
Yeah, absolutely. Yeah. So in fact, okay, she's asking a very reasonable question because okay, this is what we want to happen, right? But how do we actually get it to happen, right? And I think what you were suggesting was that in the beginning, they're just blanks everywhere, right? In fact, even this head information is not here. Everything is just blank, right? But then we tell our Turing machine, right, to just say, okay, first just write head 1 here so that I'm keeping track of where the head is. And then just keep going right. Like go right, go right, go right, go right, go right, until you see the first blank. And then replace the blank with your separation symbol, and and then go one more to the right, and then write head 2 here.
I'm sorry, I think there's just like I'm just a little bit confused. So like
Okay.
x1 to xn, it's like every time we input, we put them in there, right? Every time. Wait.
No. So once again, I just want to remind everyone, we're just assuming that our machine, it just comes preloaded. Like when you start the machine, it already has a funny symbol here, and it already has x1 up to xn on the tape. Beyond that is all blanks. So like we don't have to do that. That's like part of the definition of the machine. The machine just starts with that. That way we don't have to have like the input anymore, right? The input is just already there. Okay? Yeah. And now what she was saying is that you can just keep moving and set up the situation correctly, right? So you know where your heads are, and then you can go all the way back, and then you're kind of good to go, right? So that's great. We're getting closer to a solution, right? Let me actually or sorry, did you have a suggestion or a comment or a question?
No.
Sorry, behind you. Yeah.
Yeah, so the one that you did on the top where you have empty spaces on the main tape on the right,
Uh-huh.
I feel like in addition to, we saw the problem that even without knowing the length of the input, we were able to just kind of move right and then know where that little symbol is going to be. But also, like on the top, we're able to use the space on the right in the main tape.
Excellent. Yeah. Okay, very good. So he's pointing out a problem, right? The problem is that in the multi-tape Turing machine, we were able to use the space, right? What if our original multi-tape Turing machine actually wanted to write something here, right? Now we have this annoying separation character. Now, what you were suggesting was that you kind of move the separation character, right? So like every time you need to make space, you actually copy everything over until you get them all the blanks, right? Then you go all the way back and you say, okay, now you have a spot, right? So that was her suggestion, which totally works, okay? It's an excellent suggestion. It can work. I'm glad that you brought up the issue, which is that we have to do that. So the kind of bookkeeping that is necessary to implement her suggestion is that you would need to add this overhead. You probably actually also need some kind of like end of tape 2. Is that what you were going to say? Yeah. Okay. Maybe like #2, which just says like I'm now done with tape 2 here, right? And you can keep moving those over, right? So there's like a lot of bookkeeping that would have to be done, right? But excellent idea, definitely worth a token for pointing out that issue, okay? I see lots of hands in the air. Before I get to them, I just want to make sure, are there any questions? Like any questions about, like does everyone believe that it would work? Her suggestion would work? Does that, like it's a little vague, like we haven't like completely nailed it down. But I hope you guys all feel like it can work. Like what she's saying can work. So hopefully all of you at this point already feel like, okay, we're actually good. Like they are actually equivalent. Like you can do this emulation and it would work. It's a little complicated. There's a lot of stuff that has to happen, but it would kind of work. I don't see anything fundamentally wrong. If you don't agree with that, then raise your hand. Yes?
Wouldn't it be easier to work with 2 tapes in this scenario than working with 1 tape? Like you have 1 main tape, 1 work tape. You don't have to keep track of where the pound sign is, like to move it around, to go back.
Wait. Hold on. I want to make sure. What we're trying to prove is that a Turing machine that only has 1 tape can actually implement a Turing machine that has 2 tapes. So we are stuck with 1 tape. because like that's the challenge that we have taken on ourselves, right? Is like, is it actually any more powerful to add more tapes? And basically what she's already said together with his idea and like the stuff together is that actually no, a single tape Turing machine can just emulate a multi-tape Turing machine. There's a lot of overhead involved because you have to like keep track of where one tape ends and like keep going back and forth and stuff like that, right? But it basically does work. Again, please raise your hand right now if you just do not agree, if you feel like, wait, something is missing. Everyone feels, okay, kind of, okay, yeah.
So I just don't understand. If we can just do that with a single tape, wait, adding like a second layer, why couldn't we have just done that with the multi-tape? And if we could have done that with the multi-tape, then this is not cutting it. You know what I'm saying?
Actually, I think there's a really nice idea in there, which is not quite formulated, okay? But this is on us, right? Like we get to define, even in our single tape Turing machine, whatever gamma we want, right? What he suggested is, why don't we just make the gamma a cross product of two things, right? So we exercise that power that we had already given ourselves to implement this like second layer.
So it's not like we're really implementing the second layer. It's just that we're defining a language that way that it would be like we did it.
We're defining our Turing machine as if we did that, exactly, by means of the cross product operation, right?
Yeah, but there
Which,
wouldn't actually be a second layer, right?
what's that?
There wouldn't actually be a second layer.
Yeah, this is like, it's like, let's say that, I don't know if this is gonna help or not, but like, let's say that you're writing like a C program, right? And you had an array of like characters. And you're like, wait a second, I know a character actually has 8 bits. I'm gonna use the most significant bit as like actually a little helper, and I'm only gonna store my information in the bottom 7 bits, right? So it's just like, it's like doing something like that. Just saying like, we can actually just extend the size of a single character and just like use some upper bits of it to store some additional information, right? Yeah.
So we could do that with the multi-tape too, right? And then
We could, but again, just remember, we're trying to say that with only one tape, we can implement the multi-tape.
no, but what I'm trying to say is that with the multi-tape, we could also define the language in that way that it could do even more things, and then the single tape couldn't do those things. You know what I'm saying?
Okay. I like where you're going with it, but I want to just put that a little bit on hold for a little bit, okay? Because actually, you are saying something really beautiful, okay? So what she's drawing attention to is like the power of this construct, right? Where you just do a cross product, okay? Now, he was very modest back there. He was like, hey, why don't we just add like, no head, head 1, head 2, right? He was like, I don't want to do too much. Let's just do a little bit of stuff, right? Just add a little bit of something. But now that we know how powerful that is, maybe we can do something more with it. What do you guys think? Can we simplify this very considerably by doing even more with this? Let's kind of think about going back to square one and maybe doing something more. So any suggestion about like a more powerful thing? Yes.
If she says that we can kind of like add another row for our Turing machine by crossing it with the position of heads, can we just cross it with our tape language itself?
Exactly. Yeah. Right. Why do it just once? Let's make gamma prime, gamma cross gamma. Now we anyway have 2 tapes just waiting for us, right? And then we can also do the thing that he was saying, right? We can also still have like our no head, head 1, head 2, right?
I do have one observation about this though.
So wait. Before the observation, let me just finish just drawing it so that everyone knows what we're doing, right? So if we did this, then that is the same. That's bad. Okay. Okay. So it's like this like fat, very fat tape, right? which we're now subdividing into a very thin little top layer, and then just splitting the tape down the middle like this, right? And now we just have like tape 1. Sorry, that's really small. So like this is going to be tape 1. This is tape 2. And now we can just actually, write whatever we want to both tape 1 and tape 2 and just keep track of where the heads are. So we can have head 1 here, head 2 here. Now, the only new thing is now that both heads could be the same spot, so we could also have another thing, which is like both. Right, just in case both of the heads are in the same spot. Yeah.
When he was telling the suggestion.
And thank you, that's definitely worth a token. Sorry, yeah.
When he was telling the suggestion, what I actually imagined wasn't like 2 tapes that are put on top of each other, but like for each space of tape, like a whole tape. Like.
Oh, no. That we cannot do, right? Because this still has to be finite, right? That would be like gamma prime equals gamma by gamma by gamma by gamma, or like by gamma star, but that's infinite. We're not allowed to do that. Everything that is part of the definition of our Turing machine has to be finite. Remember, that's something we've maintained from the very beginning of the class and that we will maintain forever in the class, maybe not in the final, but in the class we will always maintain finiteness of all of our machines, okay? So with that caveat, do you guys agree? Like this is just one tape. A single symbol now has all 3 of these components, right? It's really nice, right? Really nice and elegant. Much simpler. We don't need to have any funny end of tape characters that we have to move around. A lot less bookkeeping. Still a little bit of bookkeeping, right? Like a single step of the multi-tape Turing machine would still be like a whole sweep of our new tape, right? Because we might have to update both heads. We have to kind of see where everything is, right? So there's a little bit of efficiency loss, but it works. I'm not going to draw the Turing machine because that's super annoying, so we won't do it. But like, you guys all agree that we could do it, right? So this is kind of the first major progress step that we're making, where we realize that actually a multi-tape Turing machine and a single-tape Turing machine are equivalent. And question? Yeah.
Would this mean that like one tape can represent like a matrix of like any size?
Excellent, right? So what he's pointing out is that we don't have to stop at 2, right? You could actually have any size, any finite number of tapes, right? So the same proof would work with 3 tapes, or 4 tapes, or 5 tapes, or 7 tapes, or 57 million tapes. Any finite number of tapes is equivalent to just having a single tape, right? You guys agree? And thank you, definitely worth a token. Very nice observation, right? So any finite number of tapes is equivalent to just having a single tape, which is super cool, super useful, okay? And like helps us see little by little, hopefully you guys are getting the sense that, wait a second, these things are pretty powerful, right? So the other thing, again, that you guys suggested a week ago, let me just remind you, unless there are any questions or anything. No? Yes?
When you say finite, does that mean with enough time you're able to count to that spot?
Oh, no, I just mean like an actual number, like 7 tapes, 10 tapes. Like you have to give me the actual number, and that's how many tapes we're allowed to have. It can't like grow with the input size or anything like that. Like it has to be some fixed number, just because we have to do this trick, right? So I have to be able to just define what is my gamma. And it's going to be like gamma cross gamma cross gamma cross some actual finite number of gammas, right?
I'm confused because you say that the tape itself could be semi-infinite. So I was wondering what the difference between
Yeah, absolutely. No, I'm glad you asked that question. So what we're saying is that the tape alphabet must be finite. Right? The alphabet is required to be finite because it is part of the description of like what the machine itself is. It's like part of the code of the machine, right? And that code has to be finite. The tape is infinite. It goes on forever, right? And again, even that, I would advise you to think about it a little bit differently. I'm using the word infinite a little bit loosely. It's really unbounded, right? Like you can keep going to the right, and like let's say the tape ran out at some point, okay? Then you just like go to the store, buy another tape, and attach it to there, right? Like you can just keep extending it as much as you need, right? So in that way, it's unbounded. It behaves infinitely in that sense. Does that make sense? Okay, question.
Could you kind of view it as like if your input string like keeps going in, it's kind of like if you have your original DFA and you're putting in an input string, like you don't know what states it's going to because you don't have any sense of like the memory. But this is kind of almost like now you have a buffer that like is keeping track of like what's happening when the input does something. And so it can kind of just keep generating. But like
Okay,
that's why
I'm not sure I'm completely able to follow your question, but what I will agree is that the input can be any size, right?
yeah.
The input, just like even with DFAs, the input could be much larger than the number of states that you have, right? And they just all get preloaded onto your tape, right? All of those input symbols. But even beyond that, you can keep on going further and further out, and like there's always something there, like no matter how far out you go. Does that kind of address what you were saying?
I'm kind of like trying to make sense of like the finite versus infinite nature of it, and
Okay.
so I'm thinking like you have a machine that like is just a machine that's finite that you define,
Mm-hmm.
but then as you put the input string in, there's kind of the fan going in the machine that's still doing stuff, but it's only doing stuff while you're feeding it the input. But not like we've loaded it obviously, but it's just like okay, whatever.
No, that's okay. That's okay. No, I think there's an important point I always want to make very, very clear. So remember earlier when we first started talking about like memory, right? So you should always think about it this way, that there is a finite computer, right? But then like we're attaching memory to it, right? And we're just allowed to keep attaching more and more memory whenever we want, right? So the way to think about it is this. Let's say we have our head, and the head is like moving right, moving right, moving right. And let's say this is all the memory we've bought so far only goes up to here, okay? And let's say our head is pointing here, right? And then the machine says, hey, I want you to go right, right? We're like, uh-oh, I don't have any memory. Then we just go to the store, buy another million memory locations, and just attach them, right? And they all start out blank. And then our machine is able to go, right?
Yeah.
And so basically, whenever our machine wants, not the input, but whenever our machine wants to go further, we can always just run to the store, buy some more memory, attach it, and keep going. Right? That's the way to think about it. So it's slightly different from what you were saying, but I think the same underlying idea.
Yeah.
Right? Okay, cool. Yes?
Question. We know that the power of a DFA is equivalent to an NFA. So I'm thinking maybe we can simplify the amount of tapes by just having like epsilon loops, and then we can still reach some Hodgkin
Okay.
states.
So you're bringing up something like non-determinism, like you're trying to think like, can we use non-determinism? Keep that in your thoughts. We are not going to talk about that actually for a while. But it'll come up in your homework. so don't worry, okay? It will not, you will still be able to use your thought. But for right now, I want us to just keep going a little bit further, okay? if everyone is happy with the multi-tape Turing machine, I want to again go to the final thing that you guys suggested a week ago. Okay, so one of you, I forget who it was, but one of you said, wait a second, what about a RAM machine? Right? So a RAM machine is basically this, right? Like the computer on your desk is a RAM machine, right? It doesn't have a tape, it doesn't have a head. It actually has RAM, right? And you can just write to any address, you can read from any address, and that's just how it works, right? Now, when you guys thought about it a week ago, we weren't able to completely define it, but what I claim is that now that we have multi-tape Turing machines, we can actually even define it. We could say that we have our multi-tape Turing machine. I'm just going to call it an MTM, multi-tape Turing machine. Maybe MTTM. Anyway, whatever. Multi-tape Turing machine. And again, let's say that it has like a main tape. But then it also has, let's say, an address tape. And then, oh, sorry, one more. It also has, let's say, a special, just a single character guy. This is my read-write buffer. And then finally, there's the actual RAM. Okay? And the way this works is that you can write any address you want to the address tape. There's like a special read state. Whenever you go to the read state, it looks up the address in RAM, loads it to the read-write buffer. There's also a special write tape where whatever is in the buffer gets written to that spot in RAM, right? That's basically what a RAM machine is. Now we can define it in terms of like a multi-tape Turing machine, right? So it's at least as powerful as a Turing machine because it has these tapes at its disposal, but it also has this like infinite RAM, right? Again, unbounded RAM. Like you can keep buying more RAM whenever you want, right? So you can write to any address, store it, read from any address, and do whatever you want. Does this make sense? Is that a question or? Yeah. The main tape just does whatever the control tells it to do, right? So again, this is like your DFA. And the DFA just like tells each tape, hey, move your head this way, write this, do whatever you want, write something to the read-write buffer. And they're also like there's a special read state and a special write state, okay? Yeah.
So is RAM in this case not like bound by any kind of header? So we can say address 70 if we want to write or read a certain character.
Yeah, all you need to do is just write the address to the address tape. So for example, if you want to write to position 70, you just write 70. And then just like go to the read state and like magically the 70th position in RAM gets loaded here, right? Or if you want to write to it, then you go to the right, you write whatever you want to put here, maybe a smiley face, and then go to the, so we put like 70, and then you go to the right state, and like in the 70th position, a smiley face will get written there, right?
What's the point of having these tapes at all?
It just lets us define it. That's all. Like it's just something that lets us define the notion, because if the RAM is infinite, then we actually need an infinite tape even just to write down an address, right? Like we can't write anything finitely. So just to make sense of it, we're writing it this way. All I want from you guys is for you guys to agree that okay, yeah, this is at least as powerful as a RAM machine, right? If people are convinced, then we're ready to go. And I want you guys to feel some excitement right now, okay? Because this is a RAM machine, right? This is this machine, pretty much, right? we know, you guys all know from all the classes you've already taken, this machine has C compilers. This machine has, Java compiler, whatever, your favorite programming language, Python, right? This machine can run Python, right? Everything you've learned in computer science so far, you know this machine can do, because this is the machine that you actually programmed all that stuff on, right? If we can show that a RAM machine is equivalent, let's say, to a multi-tape Turing machine, then we have crossed a really fundamental barrier in this class, right? We've gone from wimpy little toy machines, like DFAs and PDAs, all the way to like the computer on your desk, right? So with that setup, what do you guys think? How can we do that? Can we use a multi-tape Turing machine to implement a RAM machine? How would we do that? And let me just start to erase over here so that I have room. Any thoughts? So again, oh yeah, question? Mm-hmm. Yeah. I just mean like it has these multiple tapes, that's all. I wanted to just make that clear. Let me erase it because I think you're right, it's more confusing. So the RAM machine has this like DFA, it has these 2 tapes, it has a special buffer, and it has the magic RAM, right, that it has access to. Yes?
So is the question like, can we simulate the magic RAM with the multi-tape machine?
Yes, that is the question, right? The question is, we already know we can simulate the multi-tape Turing machine with the single-tape Turing machine. So we might as well start with a multi-tape Turing machine now. Can I use this multi-tape machine to simulate the RAM machine? What do you guys think? And I see, yes?
Could we say if we have n tapes, like I'm looking at the single tape.
Okay.
If we have n tapes, like top to bottom, then that is essentially the RAM machine itself.
So yeah, like as I said before, even though we can simulate any number of tapes, it still has to be a finite number, not n. It has to be like
Countably infinite, please. Countable n. How about that?
we can't do that either. Like we can do 70, we can do 100, we could do 5 billion.
Well, in that case, let's say we do 100.
Okay.
We can have 200 single tapes, the single tape machines in that case.
Okay. How will that help us implement the RAM?
So let's say the first single tape machine, right, has 100 tapes in it.
Okay.
One of those tapes is an address to the second single tape machine.
Okay. I think you just mean the second tape. Okay, so
Yeah.
let's say there's tape 2 and tape 1. Okay. And you want to like have this be sort of the address tape. I'm just like simplifying your thoughts a little bit. Okay. And I think your idea is you want this tape to sort of emulate the RAM. Is that right?
Correct.
Okay. Okay, so how would you do that? Like let's say that, someone wrote the address 70, right? How would you actually put, and then let's say right at the very beginning is our write buffer, okay? So let's say the person wanted to write the smiley face. Sorry, just want to make my smiley a little more smiley. There we go. So we want to write that to position 70. So like, how would your machine do that?
Just count on tape 2. Like start from whatever the leftmost state is. Like let's say we had another special element there.
Yeah.
Just count 70 from there. Count 70. And that's
Okay. Yeah. So what he's suggesting is why don't we just like count out 70 times, right? And just stick the smiley face there, right? So that's actually a perfectly reasonable idea, right? Just like actually emulate the RAM directly. You guys actually thought about that also a week ago. And there was only a very minor problem with it, which is that 70, let's say it's written in binary or decimal or whatever. Let's just say binary, right? You have to count out in binary, right? We haven't actually shown that a Turing machine can do that, right? Can a Turing machine count out in binary? How do you do that in binary?
Have another single tape to do the counting?
Yeah, okay. Look, first of all, it's not a bad idea at all, right? So definitely you get the token for it, right? And it sounds like it should work. There's like a very annoying little subtle point, which is just counting in binary, right? Like you guys have all done it. You guys have all figured out the algorithm for how you decrement, increment in binary, how you add and subtract in binary, right? And it's a non-trivial algorithm, right? Like it's not, I mean, you learned it in grade school in some sense, right? But like, it's not completely trivial, right? So you would need to like write down a Turing machine that with 2 tapes is able to do like binary arithmetic, right? So I would say that's the only gap. Like your idea does work. The only thing that we haven't figured out quite yet is like how to do binary arithmetic on a multi-tape Turing machine, right? I'm not saying it's impossible. I'm just saying that we don't know how to do it yet. Do you agree? Okay. So great. So you've definitely got us like, that's one option that we could go with. The only issue is binary. So we've by the way, like it was that simple, right? Like we got to this like incredibly powerful computer in a pretty simple way, right? There's like a little bit of a gap. Anyone, I'm just curious, anyone see how we might be able to avoid the binary thing? It's like yeah.
One attempt is like similar to how we did like the headers as like a Cartesian product. We can do that with like 7 natural numbers on tape 2. So we just have it indexed out already for us.
How? I didn't get it.
Like the same way we did like the Cartesian product with the headers.
Okay, so are you saying something like this? Is that what you're saying? Well, this is just not valid, right? Because this is an infinite set, and the tape alphabet has to be finite. So that's actually a very natural idea, but it's just not allowed. We cannot do that, right? Question? Yeah? Okay, yeah, good. So she's pointing out that one way to resolve this issue is just require all of your addresses to actually be written in unary, right? So just have it be like 1 to the power 70, right? Like where it's like 1 repeated 70 times. In that case, we can easily just like count it out, right? And get to the position and write the smiley face there. So that's one solution. Totally works. Worth a token for sure. It's the only objection that I have to your solution is like, that's not how this works, right? Like we actually use binary addresses in this computer, right? So let's say that I insist that no, your address actually has to be in binary, which I'll write as if 70 is binary, just because obviously we know how to convert that. This is actually kind of a cute trick. Not every year do the students come up with it. I'm going to like take a couple more ideas from you guys. If you don't see it, then I'm just going to tell you. It's a really cute idea. Again, your solution, I mean, you have your hand up, I'll ask you, but like your solution, totally valid, totally reasonable. It's just a little bit of annoying. You have to like implement binary, right? But there is actually a cute way around this. Do you have a thought?
More like a question.
Okay.
I haven't been able to wrap my head around it, but
Okay.
I was thinking of like some sort of a read-write buffer that we have for the DFA on the right side.
Mm-hmm.
Would we use that?
Yeah. Okay. No, I don't think that will lead anywhere. And also, we have very little time, so maybe I will just tell you guys. Or anyone want to try one more time? Yeah.
You just mark the end
Yeah, no, that doesn't quite work either. And the only reason that doesn't work is just because it still has to be in binary. So like in order for that to work, it just reduces the same problem. You still have to like count in binary out. One more idea? Quick. Okay, yes, how about that? I like that. Thank you. Yes, here's a quick hint. Okay? So you guys all had this like natural idea of like just directly implementing the RAM, right? Where like you actually put the smiley face at position 70. What if you didn't do that? What if you had some other data structure to hold the RAM? Any thoughts? Yeah? Excellent, right? So what he's saying is, you want to insert this? No problem. I'm just going to add open parentheses, 7, 0, comma, smiley face, close parentheses, right? And now I just know that in position 70, I have a smiley face, right? And every time I ever want to write anything, I just add a new like parentheses. It's just a dictionary map, as he said, right? So you just keep writing your new address, and then like value. You keep adding these commas, right? These dictionary positions, right? And all you have to do is just check to make sure that you didn't already use the address, which is just literally comparing character by character, right? So no binary needed. You can just compare character by character to see if you've already used the address before, right? Or just, what was that? Right, no, what I was saying is suppose that you said, okay, store a smiley face at position 70, and then the next time he said, now I want you to store a frowny face at position 70, right? So rather than like adding a new, rather than like appending 70 comma frowny face, right? We should just first check if we already wrote 70. Oh, I see. Okay. That's actually clever. All right. No. Okay. So he had an even more clever idea, which is we don't even bother to check when we are writing. We just write it always to the end. But then when we are reading, we read from the end. So we always get the latest updated address, which is a very good point. Thank you. But yeah, that's a super slick trick that works, right? And definitely worth a token. And the main point now is we have this, right? We actually have in our hands a model of computation that you guys came up with that we know is equivalent to the computers that are sitting at your desk or in your laptops, right? Which means it's not going to be that easy, right? Finding ourselves a pumping lemma, right? Like earlier, when we were trying to figure out what can't our machine do, we were always able to find some weakness, right? What's the weakness in your laptop? Well, your laptop, but imagine it has unlimited memory, right? What's the weakness in like the C programming language? What is a problem, a language problem, that no program written in C could ever possibly solve, right? And again, I don't want to like hear guesses right now, right? I want us to really think about like, how can we approach this? You know, like we need something really new, right? Like earlier, we were able to just use our intuitions and be like, oh, this machine is going to forget. Oh, this machine is going to pop and therefore forget, right? Now, we have the kind of machines we have in our on our like we have our laptop. Our laptop doesn't need to forget anything, right? It can just keep adding more memory, right? So what's the weakness? How are we going to get our hands on this, right? How are we going to think about this? I really want to, this is very non-obvious. This is going to be and I also want to let you guys know. So far, this class is beyond easy mode, all right? We are now transitioning to a significantly more challenging phase of this class, okay? As of this lecture. Because now our machines don't have any obvious weakness anymore. We have to really look at them in different ways and think of how we might be able to somehow construct some problem that no computer can solve, okay? And I think I'll just let you guys go and see you guys actually in a week, because I think we have Monday off, right? So see you guys in a week.